Okay, last class we were looking at two things: metal transfer characteristics of a consumable welding process, okay, and then we moved on to the another variant of consumable welding process, which is shielded metal arc welding, SMAW. So, metal transfer is very important because that determines the stability of the process and the productivity and the aesthetic and mechanical properties and so on and so forth. Okay, so we looked at the metal transfer characteristic as a function of varying current, right. So, at low current it is starting from globular. If you increase the current and then globular becomes rippled globular, and then there is a spray transition in which the globular and rippled globular becomes a spray transfer. Okay, so, the spray transition current is extremely critical to get the stable metal transfer characteristics within acceptable productivity, right. So, from the spray transition, if you keep on increasing the current, the drop spray becomes a jetting spray, right, and then continuously if you increase the current and jetting spray, it becomes rotating jetting and subsequently an explosive transfer. So, in GMAW the transfer characteristic is very important. So, we always aim at getting a drop spray transfer, and that is why we looked at it, right, and we also looked at the video. So, which is the most ideal transfer we always get, and this happens just above the spray transition current. So, where the droplet diameter would be similar to the filler diameter, and individual droplet with the filler diameter would transfer to the whirlpool, and this drop spray can easily be achieved by pulsing, current pulsing. So, we will see the effect of pulsing in detail in this class, right. And then if the current is increased further, then it becomes jetting spray, and jetting spray in some extent can be used for some applications where you need to have a higher melting rate of the consumables. For example, in spraying on cladding applications, you can use a jetting spray, and further increasing current lead to an unstable jetting leading to rotation of the droplets spray. And yeah, for some cladding applications we can still use an jetting or a rotating jetting spray, right. But for ideal GMAW case, the drop spray, the spray just above spray transition is very widely used, right. It is clear. And then we move on to the other variant of the consumable welding process, which is SMAW. Okay, it is also known as MMAW, the shielded metal arc welding or manual metal arc welding, or even a stick welding. So, where the welding electrode, the consumable welding electrode, it is discontinuous and it has a metal core and with flux coating, right. And most of the cases this SMAW process is self shielding process. Okay, so, we do not use an external shielding gas. So, most of the cases the process is self shielding, right. Okay. And why it is called self shielding? The self shielding because the shielding gas is generated by the decomposition of the flux, right. So, generally the flux contains the elements, they either dissociate or decompose to generate the gases. So, one of the examples I showed you in last class, the flux contain calcium carbonate based fluxes. So, these carbonate, the calcium carbonate, when you heat it up, it burns and decomposes into calcium oxide plus carbon dioxide, and this carbon dioxide generates the required shielding and arcing gas required for striking an arc and protecting the whirlpool. Okay. So, if the flux the composition is majority is made of calcium carbonate, and these kind of fluxes are known as basic fluxes. So, basically because of the basicity, right. So, it is the same, you use it in a steel making process. So, basic slags and acidic slags. Okay. So, if the flux contains primarily calcium carbonate based the composition, and this is basic slag, right. And you can also have the flux made out of rutile and some cellulosic material. What is cellulosic material? It is made of wood and wood particle. So, the natural fibers, and this cellulosic material can also be added either to basic flux or rutile based fluxes, and most commonly cellulosic materials are added with rutile fluxes, titanium oxide fluxes, because when the cellulosic material burns, what would generate? Carbon dioxide again, right? Carbon dioxide. So, you will also get carbon monoxide and then carbon dioxide when the cellulosic material burn, right. So, that provides enough carbon dioxide and carbon monoxide gases required for arcing as well as shielding. Okay. In most of the cases, so when you are welding steels with thicker sections, so we need to make sure that hydrogen is not diffused to the weld pool, right. So, for example, if you are using a low carbon steel for structural applications to build a bridge, the thickness would be 25 mm thick. In that case, you need to make sure that the hydrogen is not diffused to the pool, and whatever moisture is there condensed in the system should not lead to diffusion of hydrogen by disintegration of water H2O into hydrogen, right. So, for welding thicker sections 25 mm thick plates or even higher, so we prefer using basic electrodes, which is calcium carbonate, because when you use calcium carbonate, we make sure that the shielding gas is only carbon dioxide, right. So, the basic flux coated electrodes most commonly used for low hydrogen environment. That means that when you do not want the hydrogen to diffuse and you want to avoid the moisture condensation and then the effect of moisture disintegration. So, we need to make sure that the shielding gas is only carbon dioxide, right. So, in contrary to the basic fluxes, if you use rutile based fluxes, for example, titanium oxide is known to disintegrate water. So, for photocatalytic applications, what is photocatalytic applications? For generation of hydrogen from water, okay. So, in those applications, titanium oxide is very commonly used as a catalyst. So, photocatalytic applications. So, if you use rutile based fluxes, okay, you can also disintegrate the moisture by titanium oxide, because that is in a catalyst, very effective catalyst, and then you can also generate hydrogen, isn't it. So, because if hot water is disintegrated by titanium oxide, and then you also have cellulosic material to generate carbon dioxide. So, by binding titanium oxide with the cellulosic material, you can generate the mixture of carbon dioxide and hydrogen, right. So, for welding thinner sections, for welding austenitic stainless steels, or for welding superalloys, for cladding of hot facing stellite, cobalt chrome superalloys. So, the rutile based electrodes are all commonly used. Okay. So, these rutile based electrodes, they bring the versatility, because you do not need to bake the electrodes, is not it. Even moisture is there, titanium oxide would take care of the moisture by disintegrating the moisture into hydrogen, and hydrogen can be used for shielding. Hydrogen gas can be used for shielding. Suppose if you want to have an hot facing or welding of stainless steels, or where the hydrogen cold cracking is not that severe. Okay. The other advantage of titanium oxide is we already seen the role of titanium oxide in cost to cost variation, activated fluxes. Is known to change the surface tension of the material. So, the droplet transfer can be enhanced, the behavior can be enhanced by adding titanium oxide, because it can reduce the surface tension, for example. So, then the droplet transfer can be promoted, and also titanium oxide is act as a very active flux for the weld material. So, the weld pool dynamics can also be improved significantly. And the other one of the major advantage of using a titanium oxide is ionization, because when we looked at a GTAW electrode, tungsten electrode, they are all thoriated or the oxides doped. Okay, why? Because the ionization potential is much lower for oxides. So when you have titanium oxide in the system, so obviously you also promote ionization, isn't it? So the arc stability increases tremendously if a flux contains titanium oxide. So these are the advantages of using the rutile based electrodes than the basic flux coated electrodes. So you can have a very good arc stability because of the promoted ionization by the titanium oxide, and you can also enhance the droplet transfer frequencies because the titanium oxide also affects the surface tension of the droplets. So you can also increase the droplet transfer frequencies, and titanium oxide also disintegrates moisture in the system into hydrogen. So you also have extra shielding from the hydrogen gas. Okay, so you can also now use the electrode without baking. So generally the cellulosic and titanium rutile based electrodes, you don't bake it, because when you are baking it itself, it started disintegrating sometimes if you are baking at say 200 degrees centigrade. So cellulose and rutile containing electrodes, so it may also disintegrate during baking. Okay. Whereas in the basic flux coat electrodes, calcium carbonate containing electrodes, you need to bake, because there is no way otherwise you can fix the hydrogen. Okay. So once you have the high humidity condensed electrode, basic electrode, and you need to bake and release the hydrogen, and then you can use the electrode immediately for welding applications. Whereas if you have rutile based electrodes or cellulosic material, you can straight away start using it, okay, with the enhanced, the basic baking is not necessary, because the hydrogen anyway it is going to disintegrate from the, water is going to disintegrate into hydrogen, and hydrogen can be used for shielding, mixture of CO2 and hydrogen, right. So what are major three types of electrode fluxes we use? Rutile based, okay, cellulosic material, and cellulosic we also have some amount of titanium oxide as well. Okay. So the majority component determines the type, okay, titanium oxide plus CaCO3, and then predominantly CaCO3 based systems. So 1, 2, 3. And apart from the titanium oxide, cellulose and calcium carbonate, we can also add the allying elements. For example, if you want to increase the manganese concentration, so we can also add ferromanganese, and if you want to add chromium, you can also add chromium, ferrochromium, and those are all added in the flux the compositions. And we also need some binders, okay, to keep the powders intact, and then when you bake it, so binder evaporates. So you also have some binders added to that. Generally those are all silicates, okay, and silicates binders are commonly used for so to make the flux coating onto the electrode, right. So these are three major types: rutile based, cellulose based, and the calcium carbonate based. So
what is the difference between rutile based and cellulosic based in terms of application?
So cellulosic based electrodes are very cheap, okay. So in terms of applications, the cellulose based electrodes are used for very low end production applications, because the electrodes, we do not need to add titanium oxide or calcium carbonate. So these are very simple wood materials, cellulose based electrode materials, and these are very cheap, okay. So for very common applications like repair applications or large volume or low end applications, cellulose based electrodes can be used, okay. For high end engineering applications, generally rutile based electrodes are used, okay. So anyway, so rutile based electrodes also contain some amount of cellulose to generate, because when you have only rutile, you can get maximum about 40% of hydrogen in the shielding. So if you have 100% shielding, if you have rutile, so the maximum contribution from the rutile is only 40%. So remaining 60% should come from burning of cellulose, right. It is clear. So, cellulose burns and then gives carbon monoxide and carbon dioxide, rutile gives hydrogen, right, it is clear. So, in cellulosic material, so the majority of the shielding gas is generated by burning cellulose, which would be carbon monoxide and carbon dioxide, right. So, when you burn, I do not know, I mean, how many of you had in your younger days your mother cooking in a wood stove. So, the smoke you generate sometimes suffocating, is not it, because of increased concentration of carbon monoxide. So, when you burn wood, okay. So, this similar reaction also takes place when the cellulose based material is burnt in the electrode, you generate carbon monoxide and carbon dioxide, okay. So, that is the shielding gas. So, if you use a carbon dioxide cylinder, obviously carbon dioxide would dissociate first into carbon monoxide and oxygen atom, right. The same shielding gas can be generated by burning cellulose based material, right, it is clear. So, and then for a low nitrogen application, so where you do not need to generate hydrogen, you need to avoid the hydrogen diffusion, the basic flux coated electrodes are commonly used. These electrodes are calcium carbonate containing. So, this calcium carbonate burns and produce calcium oxide and carbon dioxide. Yes, it is clear. So, what are the fluxes we use? And apart from the shielding gas generation, the fluxes also have varying other roles, right. For example, these fluxes also do the deoxidation of the well metal, say in steel making. So, when you want to do deoxidation, okay, so what do? Yeah, so you add aluminum, so aluminum killing they call it. So, killed, aluminum killed, so that you can take the oxygen concentration out from the liquid pool. So, these fluxes would also contain deoxidizers, so typically aluminum, okay. So, aluminum, when you add aluminum burns with the oxygen and forms aluminum oxide, right. So, these fluxes would also contain some amount of aluminum for deoxidization, and you can also do desulfurization, okay, and also denitriding, okay, denitrifying, so what they call it. So, varying amount of these elements can also be added to achieve a required well metal property, right, it is clear. And some amount of alloying elements you can anyway add by adding, say, ferroalloys or even elemental alloys can also be added if the recovery is very high, but it is depending on the nature of the element. For example, you cannot add elemental aluminum because aluminum will oxidize. So, the recovery of aluminum in the well pool, it is almost very low. So, you can't alloy the well metal with aluminum from the flux or from the electrode, you always lose the aluminum, okay. So, you can try adding boron, ferroboron can be added, so boron would recover in the well pool. So, similarly alloying elements you can add manganese, chromium, silicon, ferrosilicon you can add, ferro titanium, ferro niobium, and these elements are commonly added in the well pool to improve the well metal properties, because when you add titanium, niobium, vanadium, and they are all microalloying additions, they can cause precipitates to increase the well metal toughness. So, you can play around the flux compositions to achieve the required well metal properties as well. Yes, it is clear. So, these are the roles of the fluxes. So, we will see in this class, so how these things and the role of fluxes in detail in both in SMAW and FCAW, and we will also look at the videos when these fluxes burn, how the metal transfer takes place, right, the process. Okay, good. So, this is clear, right. So, what we use in the electrodes in SMAW, so we have the metal core and then the flux coating on the top, and this is the electrode what I have in my hand. It is a basic flux electrode. So, what is basic flux electrode means? Calcium carbonate based, and if I use this electrode right away after this class to welding, so I would definitely get a cold cracking. Okay, so it is already in a very humid environment, unless I bake it to remove the hydrogen or remove the moisture, and if you weld it straight away, and then I may end up getting cold cracks. So, the basic flux coated electrode should always be baked to avoid the hydrogen embrittlement. Okay. So, if I have a rutile based electrode, right, so no, I no need to bake extensively. simple baking, because you need to reduce the moisture, otherwise the hydrogen gas generation will be higher. And then the sealing gas nature will be different, that means that arc characteristics will also be different. So, say small baking, say 100 degrees for some time, so then I can start welding, because titanium oxide will take care of the moisture. Okay, titanium oxide would dissociate water into hydrogen, and then hydrogen can be used for shielding. Okay. Same goes cellulosic electrode as well. Cellulose electrode, okay, you don't need to bake, because cellulose electrode can also contains some amount of titanium oxide, and when it burns, it generates carbon monoxide, carbon dioxide. Okay, and then titanium oxide can generate some hydrogen. Right? It's clear? Okay. So we also looked at in last class, the major disadvantage of this process is the electrode is not continuous. It has a defined length, isn't it? So the automation is difficult, or if you want to deposit continuously, so you need to make the electrode sort of a long lengthy electrode, like you make it in GMAW, like in a roll. Okay, right? So in order to do that, and also in order to efficiently produce the electrode, so we can also convert the geometry of the electrode, and we just reverse the roll, reverse the position of the flux and the electrode, and then we also make the electrode by keeping the flux inside and the metal outside. Okay, so that is what known as the flux cored electrodes, so which are something like this. Okay, so this can be made into flexible. So now the flux goes inside. Okay, so metal sheet is outside. So now we can make such electrodes, and we can make it as long as possible, and we can roll it, and then we can feed continuously. Again, the chemistry of the flux and the sealing gas generation from the flux is the same as an SMAW. You also have 3 types of electrodes, okay, basic, rutile and cellulosic electrodes, right. But the difference is here, the flux is inside, the metal sheet is outside, so it can be made into flexible. If I bend that, it will break, all the flux will go away, because flux is very brittle. In this case, the flux is very loosely packed, and even if it is, you bend it, the flux remains inside. Right, now we can make this process continuous. Right, so the process is the same. So you have a flux cored electrode coming in, okay, and then the flux insides again disintegrates based on the nature of the chemical composition of the fluxes. You may either have a CO2 generation, or CO2 carbon monoxide generation, or carbon dioxide, carbon monoxide, hydrogen generation. Right, it's clear. So okay, so then this flux again burns, it forms slag and the deposits on the top, and then you can take it off. So when you need, the other process characteristics are similar to GMAW. Right. So only thing is here the melting rate can be different. Melting rate will be different than the GMAW, because some amount of heat is also lost by the flux. Flux take away some heat. Right. So the flux also takes some heat. So the melting rate compared to GMAW in this case is slightly lower, but then most of the cases we will be using larger diameter filler. Okay, so you also generate more volume. So right, it's clear. Good.